I'm going to talk about functional infrastructures. And this talk is going to summarize our experience in using Clojure to solve a somewhat hard problem, which is how to bridge the gap between building infrastructure, which is a very wonky process, and the functional world. So the tagline was, it's all fun until you hit production, right? So let's start talking about the REPL and how we feel when we are at the REPL. We kind of feel in a state of flow. It's like playing with Legos, right? They all work together, things work, we understand it, it's interactive, and probably for most of us is where the productivity happens. Right? We spend a lot of time in a functional world. The functions that we write usually don't have side effects, and that in general makes us happy. It makes our life simple. In contrast with when we're out configuring a computer and we drop down at the shell, now things get a little harder there. Things don't always work as we expect. Things are definitely not functional, and sometimes are dysfunctional, if you ask me. So it's a complete different experience, right? We kind of lose the flow. It's a different environment. It's something that sometimes as developers we try not to do, or do it at the very end. Yes, we set up environments to develop, but we like other people to be in charge of the operations. That makes us happy. Now the question that we've been trying to solve is whether we can build a system for building infrastructure, and by building I mean provisioning the computers that we're going to use, downloading the software, installing it, pushing our artifacts into the servers. And so the question is, can we do this in a way that more or less, or how close we can get to making it functional? I contend that actually you can approximate it by this function, at least when I'm at the REPL. Right? So just apply random. So this talk is about a way to solve or to find this answer by using infrastructure automation. Now, this is not the only way to do it. Another way is, I don't know if you guys are familiar with Nixos, which is a way to try to build a functional interface to an OS, like the configuration and everything else, which is a pretty interesting project. And there are other ways to go about building infrastructure and making it functional, but this is about automating infrastructure. And what we want is to build a function, so to speak, that from the current state of the system, whatever that is, can take the system to the desired state, right? So for example, we can start from not having any infrastructure to having all our infrastructure up and running. Or we may want to, we have a Hadoop cluster with 30 nodes, and we want to make it 50 nodes. Or we just want to tear it down. Or we want to, whatever, rebalance. So I'm going to approach a little bit the history of the process of building infrastructure or automating infrastructure from two perspectives. First, I'm going to go from the bottom up, and then I'm going to go from the top down, because the way operations, and when I say bottom up, I mean operations, like from the hardware up, building automation in a cumulative way. The way developers see infrastructure and the way operations see infrastructure sometimes is not the same. We have different views, and we have also different understanding of what the problem is. And so if we start from the bottom up, the simplest case is we have to configure one box, right? So we want to install, for example, a development server that I can use. Usually when we're doing that, it's a very concrete environment. We know the hardware, we know the OS, whether it's CentOS, what version, if it's Ubuntu, what version. We know the versions of the packages that we want to install, more or less. We know the tooling, and if we don't know the exact, for example, the exact switches for a command, we just pull the man pages and we figure it out. And the way to automate this, the simplest way is either you write a script to configure that box if you want to automate, or you save an image if you're in a virtualized environment. Right? So saving an image means that you configure the server, you save it, and then whenever you want it, you can bring it back to the original state. When we're doing this, we're already aware that an operating system and the packages installed and the state of the system is just a big, big, big ball of state. Right? So it's not very functional from that perspective. Usually we have more than one box, especially in production. If not, your business is not doing very well. So when we have many boxes, now we have some requirements that we put on ourselves. We don't want to write different versions of the same script for different machines. So we want to share as much as we can. And then there are other constraints that may come down. For example, security constraints, what users are to be created in each node, what are the firewall rules. So there's some uniformity that is desired. So we want all the boxes to have certain base configuration. The way people are solving this today is by a combination of having scripts and templates that they use. Sometimes a configuration database in which you preload the database with what your desired state is and the data about that desired state, and then you run your code and your scripts, and then you have some form of a transport that will make those scripts be run on each of the boxes. Right? You may have some high-level, low-level abstractions like declarative actions for common operations, like copy a file from here to there, stuff like that. And again, you can do all these and then save your image or clone it, that's an option, or you can build the servers once they boot up, build them from code. Right, so that's kind of when people use DevOps, in general, they refer to this kind of automation, right? So it's the scripts and the configuration database, the transport. So let's look at the same problem from the top down. Let's look at it from the development's perspective. And again, as developers, we're mostly thinking at the very abstract world. We're at a very high level, building machines, building software. And we have a view, in general, I would say a big chunk of our time when we're developing, in which we don't care about a lot of the details of the infrastructure. The OS that is running doesn't quite matter. The hardware doesn't quite matter. I don't know, and I don't care how we obtain the bugs. If we are talking about clusters or even the hardware itself, we don't care that much about the size. We want it to go fast, but that's about it. We care about other things. For example, we care about being able to control our own development environments. We care about having a test environment that's somewhat connected to our let's say, Git repo and our build system, and have a stage in production. And we'd like to use the same code everywhere. If you guys ever worked close to deployment of applications in production, you know that at some point when you're running your code, when you're writing anything that's related to deploying and testing it, you want to test it in an environment that reflects as much as possible as production. And we also do development branches, right? So, and development branches are important in terms of infrastructure because that's often a thing that we don't see in the frontier between development and production, which is we develop in branches, in parallel branches, but usually our test environments, our staging environments, they only have one instance. And if our code depends in the infrastructure, then it gets out of whack. So that's the other view that as developers we have, right? So we go from not caring about any of this to caring a lot, right? For example, there's a bug in production, right? Things don't scale. Or there's a new requirement that comes from ops that we're gonna use Ubuntu for everything, where our code was developed and tested on various forms of CentOS. Or, for example, we have a set of queries that go against HBase, and now we want to switch to the newer version of HBase because it has a new feature that makes some queries faster, so we have to change our queries to take advantage of it. So now our code is tied to the particular version of HBase. So that's another instance in which we care. Or when we're getting ready for production and we know that the database that's used in production is in a hot standby configuration, so we want to see what happens when one of the server goes down. Or we want to test things like, yes, this code scales horizontally, and like how you test it, right? So now we care about the size of the cluster. We want to build a large cluster and create some load and test it. And we may have even a harder task, and somebody decides that MySQL is not performing, and we're going to change to MongoDB. So now, again, our code is tied to the particular instance of our infrastructure. And I haven't even factored the question of time. So we tend to think that we have one infrastructure at one moment in time. But if we look at code, time changes, and we may have different versions of the same infrastructure that we want to run at the same time. So for example, we have a development branch, right? So production may be in MySQL, but we as developers, we are already using MongoDB, right? It's essentially, abstractly, it's the same infrastructure, but it's a very different or a somewhat different implementation of this infrastructure. We may, as I said before, we may want to upgrade HBase and take advantage of new indexing features. Again, we want the same architecture that is running in production, but we want to be able to swap the version of HBase. And then there's other things, like there may be hotfix in productions that get put in the master line, and then we want to pick them up and bring them into our own development environment or test environment or production environment. Right? So in a way, as a developers, we like to see the infrastructure as something that you could treat just as code, and that lives with your code. So when you change your code, and I change depend on a change in the infrastructure, we want to codify that change. So it's even stored on Git in the same repo or synchronized in some way. There are other things that can happen to the infrastructure that is outside of how we use it. For example, in production, it may get more users. So we have to scale, or we may get a better deal on a different cloud provider. So we want to move our architecture, or the same cloud provider provides cheaper instances that we can use, or cheaper machines. And then, this is one of my pet peeves, is that when you use an OS, you tend to think that if you install the OS several times, you always get the same machine. But that's not the true, unless you use a persistent repository repository package system. I only know of one. So what happens here is that, I know guys, if you remember when Oracle took over Java, right? So there were some licensing issues, and all the open source package managers decided that Java was a liability, so they took it away from the package manager. So, the prior day you could just install Java from, just using apt-get Java, and the next day it was a whole lot more complicated. Right? So changes on the infrastructure come from different places, and what we know is that we're always talking about, in abstract ways, of the same infrastructure, right? It's just different implementations or different instances of the same infrastructure. So this is just this presents a problem if you want to build a platform for automation that supports every use case, or most of the use case, which is it's a combinatorial explosion.
So you have, things are different depending on the OS family, Ubuntu, Debian, Red Hat. Even in the same family, things may change from version to version. The configuration of for example, Tomcat may change from version to version. The way you wire nodes to talk to each other may change. You have different branches, so that means more changes, different environments, development, production. You may have different ways of building the same cluster. For example, if you're building Hadoop on a local laptop, you're not going to use redundant name node, but if you do it in production, you actually want to have redundant name node. So the shape of the clusters change, and even the infrastructure provided may change. Right? For example, we develop a lot on our laptops using VirtualBox, and we treat VirtualBox as a cloud provider. And when things are working in our laptop, then we just test on the cloud, and we just change the provider. Right? So it's a combinatorial explosion, and then if you factor in time, it just gets worse. Now, having said this, I mean, your problem may be a slice of this. Right? You say, well, I don't care because I can just have everyone settle on Ubuntu 10.10, and that the OS factor goes away, and the version factor goes away. But for us, as infrastructure automation builders, we care about this working everywhere. So how does Clojure help? First, let me talk a little bit about Palette, which is this automation product that we're building. And then I'll go over a few patterns of usage of Clojure, or even features of Clojure that help us bring down that complexity by using abstraction. So Palette is a functional infrastructure automation platform. It's written in Clojure. We've been developing on it for 3 years, more than 3 years. The brainchild of Hugo Duncan. He will be giving a talk later on, not on Palette. And it's used for building all kinds of services, from small services to large services, small computers, or small clusters to big clusters. And it's a large project. It's upwards of 30K lines of Clojure. We had some design constraints that we put on ourselves, as Rich Hickey said. One is that it needs to work today. This is an automation that we want people to be able to use today. And by that, I mean, we're not starting from a green field, right? You could think of ways of building infrastructure that it's easier than just using Postgres or using Nixos instead of Ubuntu. But today, that's not the case. Today, systems are very stateful. There's a lot of configuration steps that you need to do, a lot of interdependencies and versions. So we want it to work today. We wanted also that you were able to write your infrastructure code once and run it everywhere, right? That means different infrastructure providers, so either VirtualBox or a server rack that you have somewhere in your company or a cloud, right? You want to be transparent on that. On that front, we wanted also to take advantage of cloud infrastructure since the get-go and make it easy to work on that, because that's what we're seeing more people using. We also wanted to provide native support for clusters. So clusters is an interesting problem because configuring a machine is complicated enough, but newer software that we're using, Cassandra, HBase, Datomic, Hadoop, stuff like that, the configuration, there is a global view of all the machines that take part on this cluster. There are certain rules about who can SSH into which machines, or IP addresses that go in specific files. So there is a relationship between all the nodes in a cluster, and there are certain rules to obey about configuring them. If you don't do it, it just doesn't work. So we wanted to provide a native way to describe that and use it in your code. Another restriction or constraint was that we didn't want to build a framework, and we didn't want to build a server. We wanted to build a toolkit or a library, something that you can take pieces of it and build your own model
of how infrastructure should be built. For example, if you want to upgrade your software in production, there are many ways to go about it. You can do like an exponential rollout in which let's say you have 100 nodes, then first you upgrade one node and leave the other ones in the older version and wait to see what happens, and then you upgrade 2, wait to see what happens with load and everything else, and then 4 and 8. Or you may want to upgrade all at once because your application doesn't allow different versions of the same node. So if you're in a Hadoop cluster, you wouldn't be able to do that, right? It would have to be upgraded all at once. So we wanted to be able to model all these concepts. So you could build your own automation. And finally, as a library, we wanted it to make it so that you can build abstractions on top of your infrastructure. So for us, from the Palette perspective, a node is a combination of, and I'll show it later, the version, the machine that you're going to run it, and the OS that's going to be on it, and the specific steps to configure it. From the user, that's a web server, right? For the application level, at the high level, that's a web server. You don't care about the specifics. You just care about the abstraction. You have web servers, you have databases, and even then, you may have even abstractions on top of that, and the web server may be just your billing application, right? Which is a combination of a web server and certain deployed packages. So most of the people who use Palette, by the time you look at the code, you don't even know this Palette underneath. You just see the domain-specific abstractions. So Palette now takes the form of a library, which is stateless. That means you run Palette, and once you stop running Palette and the operation is done, there's no state saved anywhere. There's no database to talk to. You can run it from everywhere. And it's embeddable. So it's a jar file that you can put with your code and use it. Provides abstractions over cloud providers, hardware, OSs, configuration steps, and relationships between nodes. And it comes with a companion library of crates, which are modules that know how to configure a number of well-known services. And you can build your own crate. All right, some code. So this is an example of building a web server. Very simple. I'm showing two of the abstractions. We have a node spec, which is an abstract description of the hardware that we want to use. So this is kind of assuming that we're using a cloud provider, but it'll work everywhere. And we say, well, I want a node that has an image that is Ubuntu 10.04, and I want machines that have 12 nodes and 64 gigs of RAM. Right? And then you say, okay, so I'm going to define a group. So a group in Palette is a set of machines that are configured identically. So I'm going to define a group, and I'm going to say, use that spec, that node spec, and configure it in the configuration phase, and there could be many phases, but the configuration phase, install Java, install Tomcat. Right? That's simple. Then we need another abstraction, which is the compute service. So we're saying, EC2 is just a connection to Amazon's EC2 cloud provider. And then we issue a command called converge, and we say we want 5 web servers built on EC2. Right? That's all we do. But we can take it a little bit farther, and that's where the functional aspect comes in. Before I was using concrete specs, but they don't have to be concrete. They can actually be just, it's all data manipulation at this point. So we can build a function that will build a node according to our specs based on parameters, right? So a web server, you specify the CPUs, the RAM, the OS family, and OS version. And then the group spec can also be defined functionally and based on the same parameters. So now we have a function for the group web servers that builds a spec based on these specific parameters. So at the top, now we're converging, and instead of, so we're passing a map of a group that is created on the fly, right? So this group doesn't exist. We call a function that returns all the specs that we need, and then we say build one of those on EC2. So this is equivalent at this point to what we did before. But when things get interesting is, for example, let's say you want to test on different OSs, right? So we say, okay, let's make a vector of
OS families and versions, right? And then let's build, let's make a function that will build, given a map, given that vector, is going to build a set of group specs, right? And then we can just converge them all at once, right? And normally we can do that on EC2, but then if we want to do it locally in our environment, we can just build it on VirtualBox, right? So this is where things start to get functional. So as I said before, Pilot is serverless, and since there's no server, there's only code and files, you can actually put your infrastructure automation in Git along with your code, right? So if your code changes and uses MongoDB, then your infrastructure changes and uses MongoDB. So there's no point in time in which you have your own development environment and then someone else has to test your code and now needs to know how to build the environment. You building your environment on progressively as your code evolves. You can build your own abstractions on top of Pilot. You can embed Pilot in your applications, and this is important because if you're a product vendor and you want your product to be deployed everywhere, you probably want to encapsulate all this and put it inside your product and ship it. You can also, inside a company, if it's a large company, you can distribute automation bits as jar files. So for example, you have your own server that is internal to your company and somebody built the crate for that server, then you can put that crate. You don't have to share the code. You can just share the crate and put it in your Maven repo or your Clojure repo. It would be better. And then someone else can depend on that in their project and say, give me the crate for such a service and then use it. You don't have to share the code. And that means that you can also version it and so on and so forth, all the properties that software has. You can also describe and build your infrastructures in a generative way, right? So you don't start from a concrete representation of your infrastructure, but you start with an abstract representation of your infrastructure, and then you pass some parameters about what it is that you want, and then that creates the concrete version, and then creates it in real life. And write once, run everywhere, and I'll show a little bit of that. So what are the things in Clojure that we use? We use DSLs. DSLs are a great way, and I think we've seen a couple presentations at least, Piplin and the one about LLVM, in which the use of a DSL let us bridge between two very different worlds that don't quite match. And Pilot has a DSL named Stevedore that abstracts over scripting languages and tooling. So with Stevedore, if you have your Clojure code, you have Stevedore library, which is an independent library, by the way. You can use it without Pilot. And an information about the target, like the Ubuntu 10.10, it'll build a correct script for that platform, right? And if then you say, hey, I want to use it in a different platform, it'll get you a correct script for that platform that will be different sometimes from the first script. Stevedore also lets you intertwine Clojure code with shell script code, which is very powerful. It lets you build your scripts in a very concise but abstract way. And I hope I'll show just a tiny bit of that. So Pilot itself is built on Stevedore. And every time Pilot talks to a machine, it does it via Stevedore. So all the actions that Pilot does on the servers are determined dynamically based on the characteristics of the target servers. And also in Stevedore, there's the concept of script abstraction. So you can create scripts that use other scripts and so on and so forth in a very Clojure-like way. So let's see if I can do the demo, because I was having, there you go. All right. Do you guys see it well? Is it too big? Can I make it smaller? A little bit. Like this? Is it good? All right. So I have, I'm really bad at typing, so I'm just going to copy paste. And I'm sure that there's a correct way of doing this in Emacs. But
All right, so the simplest form of stevedore, this is a function. This is just a helper function to use during development is print hello world. So it gives us the shell script way of doing it, right? So this is a different case. Here we're building a iteration over 4 values and just printing each value, right? So we run this, and this gives us the shell script form. Pretty easy. Pollet has a bunch of predefined scripts in a library, and you can actually build your own. So for example, I'm going to show the create user. Now this is OS specific, right? So I'm going to create a user that belongs to 2 groups. And I want to see what happens if the OS family is sent to us, right? So it just does user add.g with the groups and my name. But what if, what if I do it on Ubuntu? Right? You spot the difference? Not big, but enough to break your scripts, right? So this is the first form of abstraction that we use in Pollet. Let's see, there were more scripts, but theoretically, you have to come to us with a big suitcase full of dollar bills, and we'll gladly do that. All right. Now let's see if I can get. By the way, I know how to switch with Command Tab. It just stopped working. All right. So what else? We use multi-methods. So multi-methods are also very good for our use case because it lets us express abstract concepts that have very different representations, right? So just as we saw before, well, that was probably not a good example, but CentOS and Debian, they differ in the tooling a little bit, just enough, but there are other things that differ very much, and we'll talk about it a little bit. But one of the things that we like about multi-methods is that they're open for extensibility. So let's say we don't support your favorite niche flavor of Linux, right? We never tested it. Well, you can actually provide the method implementation for your OS. You're specialized when Pollet is guessing it wrong because it doesn't know how to use your OS, you can actually extend Pollet without going inside the code, right? Which is important. Another use case is that you're using a version of some OS that has a bug. And you say, wait, when you do a sudo in this version of whatever, actually pass this parameter because if you don't do it, it's going to break. So open extensibility allows us to extend most of what Pollet does without touching Pollet's code. So an example of using multi-method, as I said before, sudo can be done differently. It's going to be working differently between CentOS 5.3 and 6. Java is installed differently depending on the OS family and version. And now, thanks to Oracle, is installed very differently depending on the OS family, the OS version, and the version of Java, and whether you're installing OpenJDK or installing Oracle JDK, right? So this is a place in which all you want is to install Java, and there's multiple ways of going about it that are just not so dependent on the nitty-gritty of the script, but it's the higher level process. Data. Data is perfect, right? It's a perfect, simple tool to do a lot of work, a lot of heavy lifting, and very simply and very fast. It's easy to test, it's easy to inspect, debug, log, and the trick to using data is to live in the data world for as long as possible. That means deferring execution as much as you can. And Pollet internals are built around data. So most of the Pollet's code itself is just data manipulation or code manipulation. So, so one of the advantages of that, is that the components inside Palette are quite loosely coupled, and the connection between them is just data. So it's easy to test one specific component by just feeding data in and getting data out. I showed before how the abstractions in Palette are described as data. So basic abstraction in Palette are maps, and we have a form of doing mixins that I'm not going to show. I want to talk a little bit about the compilers. So Palette is built like a compiler in a way, not intentionally, but that's how it happened. And in which you start with a description of your target architecture, which is kind of like your code. And then we build an abstract representation of what you meant. And then we massage that abstract representation, but it's all data all the way until the very end, in which we actually turn that data into shell scripts and execute them, right? So Palette works in these two ways. You have a function called lift that takes the current state and builds a plan. Then we massage the plan, and then we have another step, which is the execution of the plan, right? And that's what converts the plan into actual shell scripts, and then runs them against the system, and that gets us the desired system. All right, so last demo. So I'm going to use a function called explain plan on automated admin user. Oops, it's back. All right, so automated admin user is it's a create function that what it does is when a machine boots, it goes, gets your SSH credential and authorizes you in that machine so you can SSH passwordlessly with it. And then it adds you to the sudoers group and gives you permission to operate on that node. So explain plan gives us this, it converts into an abstract definition of a set of actions, like install the package sudo, create a file, create my home, create a directory, run a script to authorize my key, so on and so forth. If I run the same thing and say print scripts true, right? Now it's not only going to give me that information, but it's also going to give me the shell scripts that it's going to run, right? So for example, the authorization of the key, this is the script it's going to run. And you can notice that there are markers here that tell us where this code, this specific part of the shell script comes from. Right? So you can inspect those scripts and then go back to your code and see how they were generated. Okay. All right. There we go. Okay. I'm going to run fast through this because I'm running out of time. We use state machines, which are perfect for separating, for understanding better the execution steps that you're running and the state of the configuration. And lets us separate state from execution. And it also let us abstract the biggest functional pieces of Palette, so you can compose them in a different way. We use concurrency a lot. So immutability and closure is great, but for everything else, there's atoms and refs. And 99% of Palette is stateless, but we use state in specific places because we tried monads and people didn't like it. They were too hard on the users. We still use monads internally, but you don't have to know. Another advantage of closure is that it's the JVM. So it's, you can access well-tested, well-understood performant libraries. Doesn't matter, we have closure, so we realize we don't use that many, we use 3. One of them is optional. One is JClouds, which is to access the cloud providers. The other one is SLF4J for logging, and GSSH, CH for SSH. And that's it. Those are the only direct dependencies. And as I said before, being in the JVM means that everything can be a jar and everything can be put in a Maven repo. So have we achieved this? To some extent. I mean, it's not perfect. You still state to deal with, but we're getting there. We have this functional infrastructure, works pretty much on every OS and every cloud. People are building complex infrastructure with it today.
We're providing fast development paths, like the explain plan that I showed, and it's easy to build abstractions on top of it. So what are we doing with it? So as a company, we're building what's called Palette Big Data, which is still in early stage. But the idea is to automate everything big data. And we have a prototype working of an EMR replacement. So if you use Amazon and, for running your Hadoop jobs, you may want to take a look at what we're doing. Just send us an email. But our goal is to actually build every piece of big data infrastructure and provide a high-level abstraction on top of it. That means a user interface with buttons. We built Brick Layer because we didn't want to use Hudson. So we built it's like Git, but for builds. So you can have you build information and scripts embedded with your code. So somebody downloads your code and automatically can build your product and deploy it. And as Hugo showed yesterday in the Lightning talk, we have Palette Up just as a companion for Lightning in for the same concept of building infrastructure. And that is all for me.